Imagine standing at the rim of a crater near the moon's south pole, looking down into a darkness so complete that it has not been touched by a single photon of sunlight in more than 3 billion years. Not dim, not shadowed the way a valley is shadowed on a cloudy afternoon. Fully, permanently, absolutely dark, sealed away before the first living cell ever divided in Earth's oceans, before the continents took the shapes we recognize, before almost anything we would call biology had begun. The floor of that crater has been sitting in perfect stillness, at temperatures colder than the surface of Pluto, for longer than most of the history of complex life on this planet. And we have been sending missions to the moon for over 50 years, and we still cannot tell you with certainty what is down there. That is the paradox that should stop you for a moment. The moon is the most studied object beyond Earth. We have walked on it, driven across it, crashed probes into it deliberately, bounced lasers off reflectors left behind by astronauts who are now in their 80s. We have maps of its surface at resolutions that would let you spot a dining table. And yet, the question of whether those permanently shadowed craters hold water ice, real, usable, frozen water that could sustain human outposts and, stripped into hydrogen and oxygen, fuel rockets deeper into the solar system. That question does not have a clean answer, even now, even after all of that. And the reason it does not is one of the stranger stories in the history of space exploration. Because right now, several nations are pointing hardware at that southern darkness and preparing to find out for themselves, which means whatever is hidden down there is about to become the most contested ground beyond Earth's atmosphere. If questions like this one are what you find yourself wanting to sit with late at night, like and subscribe so you do not miss where this goes. Let's begin. The strange story begins in 1976 with a Soviet spacecraft called Luna 24 and 170 grams of soil. That number deserves a moment. 170 grams is roughly the weight of a baseball. The kind of object you could close your hand around without thinking about it. Lighter than a coffee mug. Lighter than most of the things sitting on the desk in the room you are in right now. A Luna 24 had drilled nearly 2 meters into the lunar surface, deeper than any sample return mission before it, pulling a core of compacted regolith up from beneath the dust and rock of the moon's equatorial region. The spacecraft then launched from the lunar surface, rendezvoused with no one, crossed the 384,000 kilometers back to Earth on its own, and landed in Siberia. Scientists recovered the canister. They opened it, and inside, in that baseball's worth of ancient compressed soil, pulled from another world, they found something that should have changed everything. The samples contained water, not a flood of it, not a dramatic soaking, 0.1% by mass, which sounds almost negligible until you consider that this was a reading from material that had been sitting in hard vacuum, under no atmospheric pressure for billions of years. 1 part in 1,000, which is a small number right up until you consider that the standard assumption at the time was 0, not approximately 0, not less than 1%, 0. The prevailing scientific consensus held that the moon was completely, definitively bone dry, a world that had been baked sterile by 4.5 billion years of unfiltered solar radiation, stripped of any volatile compounds long before the first Apollo astronaut ever set foot on it. And then Luna 24 returned with a reading that said otherwise. What made the finding harder to dismiss, and what should have made the scientific community slow down and look more carefully, was the pattern inside the core sample itself. The water concentration was not uniform across the full depth of the drill. It increased with depth. The deeper the material had come from, the more water it carried. That is not the signature of surface contamination, where a spill or a breath of humid air touches the outermost layer of a sample before a researcher can seal it. Contamination sits at the surface. It does not grow more concentrated 2 meters underground in material that has never been in contact with Earth's atmosphere. The geometry of the reading was pointing at something real. The finding was published. Soviet scientists reported it in the literature, and then, for the most part, the broader scientific community set it aside and moved on. The explanation given was terrestrial contamination. The idea that somewhere in the recovery process, and in the handling of the canister, in the opening of the sample, moisture from Earth's air had found its way in and produced a false reading. It is a reasonable thing to check for. Contamination is a genuine problem in planetary science, and dismissing a single reading from a single mission, especially a Soviet mission during the Cold War when Western scientists had limited access to the raw data and methodology, was not an unreasonable first response. The problem is that the first response became the permanent response. No one followed up. No mission was designed in the years that followed to specifically test whether the reading was real. The finding sat in filing cabinets and journal archives, cited occasionally, never seriously pursued, because the textbook already said the moon was dry, and one anomalous reading from one Soviet mission was not enough to rewrite the textbook. This is the pattern that medicine has encountered over and over again across its history, and it is worth understanding it clearly here, because it explains something important about the next 3 decades of lunar science. When a field reaches consensus on a question, not through an exhaustive process of testing and elimination, but through an early assumption that hardens gradually into received wisdom, the consensus itself begins to function as evidence. New data gets evaluated, not on its own terms, but against the background of what everyone already believes to be true. A result that contradicts the consensus gets a higher burden of proof than a result that confirms it. Her contamination becomes a more persuasive explanation than the possibility that the textbook is wrong. Not because the contamination hypothesis is stronger, but because it leaves the textbook intact. The entire field had agreed, on relatively thin grounds, that the moon contained no water, and so every signal that suggested otherwise became, by default, an error to be explained away rather than a clue to be followed. 170 grams of soil from 2 meters underground on another world, carrying a water signal that grew stronger with depth, not weaker. And the answer the scientific community settled on was, we must have breathed on it. That dismissal was not an isolated event. Luna 24 was not the only piece of evidence that arrived and was set aside. Which means the question of how the dry moon consensus survived for as long as it did goes considerably deeper than one Soviet mission in one Siberian recovery zone. Because Luna 24 was not the anomaly. That is the thing that gets buried in the way the story is usually told. The Soviet mission, the Siberian landing, the 170 grams of soil, it all gets framed as a single disputed reading from a single disputed source, which makes the contamination explanation easier to accept. But years before that canister touched down in Siberia, American scientists were sitting with 382 kilograms of lunar material brought back across 6 Apollo missions between 1969 and 1972, and those samples were telling a version of the same story. In trace hydrogen-bearing compounds, signatures consistent with hydroxyl, the molecular building block you would expect to find if water had once been present. Not definitive, not in large quantities, but there, in the readings, repeated across samples from multiple missions, collected across multiple years by multiple crews from multiple landing sites scattered across the lunar surface. The researchers who encountered these signals did what researchers do when the data contradicts the consensus. They attributed them to contamination and moved on. The samples went into storage at NASA's Johnson Space Center, catalogued and preserved and largely unexamined on this particular question, because the textbook said the moon was dry and the textbook was not under serious challenge. Imagine finding a note in your house that says there is gold in the basement. You read it, find it implausible, and drop it in a drawer. 10 years later, someone else finds a note in a different room saying the same thing. You dismiss that one too. Different handwriting, different source, probably a coincidence. Then a third note, then a fourth, in a box you have had since before you moved in. At some point, the question is no longer whether the notes are reliable. The question is why you keep explaining them away instead of walking down the stairs. The Apollo samples were not one note. They were dozens of readings, across dozens of individual sample containers, from 6 separate missions carried out over 3 years, representing the largest collection of extraterrestrial material in human history. And the answer the field settled on, here consistently, was contamination. We must have let Earth's atmosphere in. We must have introduced moisture during handling. The notes keep appearing and the basement goes unchecked. This is the first pattern worth noticing. Not a failure of instruments, a failure of imagination. The dry moon consensus survived for more than 30 years despite these signals. Not 3 years, not a decade. 30 years during which no mission was designed specifically to test whether the readings were real. During which the question of lunar water was not treated as open. During which an entire generation of planetary scientists was trained on the assumption that the answer was already known. 30 years is not a brief oversight. 30 years in a scientific field is long enough for the original assumption to become invisible, not a hypothesis anyone is defending, but simply the background condition against which all new work is measured. And here is where the geometry becomes important, because there is a reason the dismissal was so comfortable for so long. And it has to do with where anyone would have thought to look. When you imagine the moon, you probably imagine the version that has been visited, the equatorial and mid-latitude regions, the places where Apollo landed, the flat volcanic plains and rubbled highland slopes that received the boots of 12 human beings. Those regions are exactly what the dry moon hypothesis predicted. They are exposed to unfiltered solar radiation for roughly 2 weeks out of every lunar month, are baked to temperatures above 100 degrees Celsius during lunar daytime, and then plunged into deep cold at night. Any water molecule that wandered onto that surface would be broken apart by ultraviolet radiation within hours. The conditions there are genuinely hostile to water in any form. So when you sample that terrain and find almost no water, the dry moon conclusion feels natural. It feels like you have simply confirmed what the environment would obviously produce. But the moon's axial tilt is approximately 1.5 degrees. Earth's is 23.5 degrees, and that tilt is the reason we have seasons. The reason the northern hemisphere leans toward the sun in June and away from it in December. The reason summer exists as a concept. Yet the reason the poles receive sunlight at an angle that changes throughout the year. Remove that tilt and the poles stop cycling. They stop tipping toward the sun. The light arrives from the same direction, at the same angle, forever. The moon, with its 1.5 degree tilt, is almost perfectly upright in space. And what that means for the landscape near its poles is something that takes a moment to fully register. It means there are craters at the lunar South Pole and North Pole whose floors have never once been touched by direct sunlight. Not in 1,000,000 years, not in 1,000,000,000 years, not since the craters were carved into the surface by impacting objects billions of years ago. Their geometry, deep bowls sitting near the top of a world that barely tilts, places their floors permanently below the horizon relative to the sun. Yet the sun skims along the crater rims, but the light never reaches the bottom. Some of these regions have been completely dark for 3.5 billion years or more, which means they were dark before the first complex cells appeared in Earth's oceans. Dark before the atmosphere of this planet contained enough oxygen to breathe. Dark for a span of time so vast that the entire history of animal life on Earth fits inside only the most recent fraction of it. A water molecule that migrates from the sunlit surface into one of those craters does not evaporate. It does not get split apart by radiation it can no longer reach. It freezes, instantly and completely, against the crater floor, and it stays there. This is called a cold trap, and the physics of it is straightforward. The temperature in the deepest, permanently shadowed regions drops to around -240 degrees Celsius, colder than the surface of Pluto, colder than almost anywhere else in the inner solar system. And at those temperatures, the vapor pressure of water is so low that a molecule of ice essentially cannot escape. It is locked in place by the thermodynamics of extreme cold, held in a darkness that will not lift as long as the moon's geometry remains what it is. Every comet that ever struck the moon, every asteroid carrying hydrated minerals, every passing cloud of interplanetary gas could have contributed water molecules that drifted toward the poles and disappeared into that cold. And over billions of years, those molecules could have accumulated. Because the conditions for preservation were there, scientists stopped dismissing the signals and started asking where, on this world, water might still be waiting. So scientists stopped dismissing the signals and started pointing instruments at the right part of the sky. That sounds like progress. And in one sense it was. But what they found when they looked was not a clean answer. What they found was a series of doors, each one opening onto another door, each one promising that the room behind it held the answer, and none of them ever quite opening all the way. The first piece of this was understanding just how cold those shadowed craters actually are. We said the temperature drops to around minus 240 degrees Celsius, and that number is accurate. But it turns out it undersells the situation considerably. When the Lunar Reconnaissance Orbiter began returning detailed thermal data from its Diviner instrument, the coldest readings from the deepest permanently shadowed regions came in at around 25 Kelvin. That is minus 248 degrees Celsius. And a Kelvin, for context, is a unit measured upward from absolute zero, the theoretical floor temperature of the universe, the point at which molecular motion effectively stops, the point below which there is nothing. 25 Kelvin is 25 degrees above that floor. Pluto, which sits 5.9 billion kilometers from the Sun, so far that sunlight takes more than 5 hours to reach it, has an average surface temperature of around 44 Kelvin. The permanently shadowed craters near the lunar South Pole are measurably, significantly colder than the surface of Pluto. Sit with that for a moment. The coldest places we have ever measured in the solar system are on our nearest neighbor. You could theoretically drive to one of these craters from a future lunar base in a matter of hours, and yet the floor of that crater would be colder than a world so distant that humans spent decades arguing over whether it even qualified as a planet. The hostility of the environment does not match the proximity. Something that close should not be that extreme, and yet the geometry of the moon's tilt and the depth of those ancient bowls produces a cold that is genuinely among the most severe anywhere we have measured. And at 25 Kelvin, water ice does not just persist. It persists essentially forever, a locked-in stability so complete that molecules frozen into the crater floor billions of years ago would still be there, unchanged, waiting. So the question was how to confirm that they were actually there. In 1994, a joint NASA and Department of Defense mission called Clementine spent about 2 months mapping the lunar surface in remarkable detail, and it confirmed the geography. It confirmed that permanently shadowed craters existed at the South Pole, that their floors were below the solar horizon, that the cold trap conditions were real and extensive. Clementine drew the blueprints with precision. What it could not do was look inside. The mission carried no instruments designed to detect ice or hydrogen, and so it returned with a map of containers that might hold something extraordinary and no way to open a single one of them. The geography was confirmed. The contents remained unknown. It was, in a very particular way, one of the more frustrating half-answers in planetary science, to arrive at the vault and be told that yes, the vault is real, and then discover you left the combination at home. Lunar Prospector, launched in 1998, took the next step. It carried a neutron spectrometer, an instrument that detects the presence of hydrogen by measuring how incoming neutrons from cosmic rays are slowed down when they strike hydrogen atoms. Hydrogen is lighter than most elements, and a neutron striking a hydrogen atom slows more efficiently than one striking heavier atoms. The same principle that makes water an effective neutron moderator in nuclear reactors. When Lunar Prospector passed over the poles, it detected elevated hydrogen concentrations. The signal was real, consistent, and repeated across multiple orbital passes. And from that signal, scientists attempted an estimate, somewhere between 10 million and 300 million metric tons of potential water ice distributed across the polar regions. That range tells you almost everything about where the science stood. 10 million to 300 million is not a refined estimate. It is a confession that the measurement technique could confirm something was there but could not tell you what it was, how much of it existed, or whether it was water at all. A hydrogen trapped in mineral crystal structures would produce the same signal. Hydroxyl, a water molecule missing one hydrogen atom, would produce the same signal. The neutron spectrometer could not distinguish between them. The range of 30 times between the low and high estimates was not a failure of the instrument, so much as a fundamental limit of what hydrogen detection alone could prove. And so, NASA made a decision that, in retrospect, has a certain desperate logic to it. When Lunar Prospector ran low on fuel in July of 1999, rather than simply allow it to drift and go silent, mission planners aimed it at a permanently shadowed crater near the South Pole and crashed it deliberately, at speed, into the floor. The idea was that the impact would excavate material from the crater, it'd throw a plume of debris into sunlight above the crater rim, and that Earth-based telescopes trained on that spot would detect water vapor in the ejector. It was the most direct test available. It was also an act of destruction of a spacecraft that had cost hundreds of millions of dollars to build and launch, smashed on purpose against a surface it had spent a year faithfully mapping, in the hope that the explosion would finally break open the answer. Earth's telescopes watched the impact site. They detected nothing. No water vapor, no ice signature, no visible plume at all, at least not one containing anything they could identify. And still, the moon gave up nothing. The crater floor absorbed the impact and returned silence, the way a question disappears into a room where nobody is listening. And the whole planet watched from 238,000 miles away and saw only darkness where the spacecraft had been. That was not the end of the impact approach. Japan was preparing a mission of its own, and it would bring its instruments to the same problem from a different direction entirely. Japan had been watching all of this. They had seen Clementine confirm the geography and come home empty-handed. They had seen Lunar Prospector detect hydrogen it could not identify, then end its life against a crater floor that swallowed the collision and offered nothing in return. And so when Japan launched their own lunar orbiter in September of 2007, a mission called Kaguya, also known by its scientific designation Selene, they brought instruments that Clementine and Lunar Prospector had never carried, including high-resolution cameras capable of mapping the surface in detail that earlier missions could not approach. Kaguya spent nearly 2 years in orbit, building a picture of the moon with a precision that still stands as one of the most thorough photographic surveys of any world beyond Earth. And when the mission ended in June of 2009, controllers guided the spacecraft into a controlled impact near the South Pole, deliberate, measured, aimed at the same class of permanently shadowed terrain that the previous crash had targeted. The impact happened. The crater received it. And still, the moon gave up nothing. That sentence is harder to absorb the third time through, when the pattern has had time to settle into something heavier than coincidence. This was not one mission stumbling. This was not a single instrument limitation. This was 2 spacefaring nations, separated by language and history and engineering tradition, both arriving at the same dark terrain, both choosing destruction as their method of interrogation, and both receiving the same answer, which is to say, no answer at all. 2 crashes, 2 silences, and behind each silence, the same unresolved question that had been accumulating since Luna 24 returned its core sample from Siberia in 1976. The pattern was no longer a streak of bad luck. It was starting to look like a statement about the approach itself, as though every attempt to force the moon's hand by colliding with it was simply inadequate to the scale of what was being asked. You could throw a spacecraft at that crater floor, and the crater would absorb it the way a deep ocean absorbs a stone, completely, without commotion, without disclosure. And then India launched Chandrayaan-1. The mission went up in October of 2008, carrying instruments from several different space agencies, and among those instruments was a small impactor probe, the Moon Impact Probe, built by the Indian Space Research Organisation, designed to separate from the main orbiter and fall toward the lunar surface. The descent lasted 25 minutes. That is not a long time. 25 minutes is a lunch break, a short walk, the length of a television episode without commercials. But in those 25 minutes, as the probe fell toward Shackleton Crater near the South Pole, its instruments detected water molecules in the lunar exosphere, the thin, nearly imperceptible envelope of gas that clings to the moon's surface. Not a hint, not an ambiguous hydrogen signal requiring interpretation. Water molecules, detected directly during a descent that covered what orbital passes had only been able to survey from a distance. In 25 minutes of falling, that probe found what decades of orbiting had approached but never confirmed. The detection was real, it was specific, and it arrived from a direction that nobody had fully anticipated. Not from the crater floor itself, but from the air above it, thin as that air was. But that was not the finding that changed everything. Aboard the same orbiter, NASA had contributed an instrument called the Moon Mineralogy Mapper, referred to in the mission documentation as M-cubed. And M-cubed was scanning the surface in wavelengths that could identify the spectral fingerprints of specific molecules. What it found, when the data came back and was processed and checked again, it was water and hydroxyl not confined to the permanently shadowed regions, not hiding in the darkness that had been cold-trapping molecules for billions of years. The signal was appearing on sunlit surface, on terrain baked directly by the sun, across latitudes that had no business holding water by any theory that had guided the previous 4 decades of lunar science. Water was not just in the shadows, it was everywhere, faint, distributed, appearing and disappearing in synchrony with the sun's movement across the surface, as though the regolith itself was absorbing and releasing water molecules on a daily cycle, breathing them in from the solar wind or the thin exosphere and exhaling them back out as temperatures climbed. The pattern was not random, it was correlated with the sun. Higher concentrations appeared toward the poles, where temperatures were lower, but traces showed up even at equatorial latitudes in the cooler parts of the thermal cycle. Every place the instrument looked, it found something that should not have been there under the dry moon model that 30 years of consensus had treated as settled. This is not a simpler answer than no water at all. Finding water only in the permanently shadowed craters would have been a clean problem, difficult to reach, but at least contained, at least understandable, within a mechanism that science had already worked out. Finding it everywhere, faintly, cycling with the sun, meant that the question of where lunar water came from and how it behaved had just grown wider at the same moment it had, for the first time, received a genuine confirmation. The signals were multiplying. Yet what scientists needed was not another hint, they needed proof, and the next mission was designed to get it by force. So NASA built a hammer, not a metaphorical one, a literal instrument of force, a 2.3-ton Centaur upper stage rocket body stripped of its fuel and aimed with deliberate precision at Cabeus crater near the moon's south pole. The year was 2009. The mission was called LCROSS, Lunar Crater Observation and Sensing Satellite, and its entire scientific logic rested on a single premise. If there is water ice frozen in that permanently shadowed crater, an impact large enough to throw the contents of the floor into sunlight will reveal it. The crater would not be able to stay silent if the right question was asked at sufficient velocity. After lunar prospector's silent crash a decade earlier, after Kaguya's controlled impact that returned nothing, after 30 years of signals that multiplied without ever arriving at confirmation, the approach had changed. The mission was not asking the moon to volunteer its answer. It was designed to extract one. The Centaur stage hit Cabeus at roughly 2 kilometers per second. A trailing spacecraft flew directly through the ejector plume that the impact threw up, the material from the crater floor that had not seen sunlight in somewhere between 3 and 4 billion years. And its instruments read the cloud in real time, cataloging the molecular signatures of everything the impact had released. The result was unambiguous in a way that no previous detection had been. Water vapor, hydrogen, and then, alongside those, something that nobody had built their predictions around: ammonia, methane, carbon monoxide, carbon dioxide, not just water, a chemical inventory that read less like a simple ice deposit and more like the frozen residue of the early solar system, volatile compounds that had drifted in from comets and asteroids and interplanetary gas clouds over billions of years, settling into the one place on the airless moon cold enough to hold them. The permanently shadowed craters were not just water traps, they appeared to be time capsules, preserving a record of what the inner solar system was made of during its most chemically active period. The first unambiguous confirmation of water ice in a permanently shadowed region had arrived, and the vault, after decades of standing silent, had finally opened. And we hadn't even started digging. But even the opening of the vault came with complications, and the first one was quiet. The ejector plume was dimmer than the models had predicted. Not catastrophically dim, The water was still there, still confirmed, but the brightness of the plume, the density of material it threw into sunlight, was less than the simulations had calculated based on what scientists assumed the crater floor was like. One explanation that emerged from the analysis was that the regolith inside Cabeus might be unusually porous, loose, almost fluffy in its structure, more like the surface of a snowball that has partially sublimated and refrozen than like the compact, granular soil of the sunlit lunar surface. The floor of the shadowed crater had never been heated, never been compressed by the same thermal cycling that repeatedly bakes the equatorial soil. It had just been accumulating, cold and undisturbed, for billions of years. The physics of the impact did not behave as predicted, which meant that the physical properties of that soil were different from what the models had assumed, which meant that whatever was down there was harder to characterize than a single successful impact had revealed. The estimate for total polar ice that emerged from combining the L-Cross data with everything Chandrayaan-1's instruments and the Lunar Reconnaissance Orbiter had gathered came to roughly 600 million metric tons. That number is large enough that it is worth holding for a moment before accepting it and moving on. 600 million metric tons of ice is approximately 600 billion liters of water. If you were to fill Olympic swimming pools, which hold about 2.5 million liters each, that quantity of water would fill roughly 240,000 of them. That is a substantial reservoir, and anyone thinking about future human presence on the moon would be right to feel a shift in what seems possible. But the number rests on a premise that matters enormously. It assumes the ice is present throughout the polar regions in the same concentrations that L-Cross found in a single crater during a single impact. 600 million metric tons distributed through billions of tons of loose, porous regolith, mixed grain by grain with dust and rock, is a fundamentally different engineering problem than 600 million metric tons pooled as accessible ice sheets. You cannot pump dispersed ice. You have to mine it, heat it, process it. The total figure sounds like abundance. The physical reality of how that water might be distributed sounds like a much harder problem. That is the gap we are talking about. And then M-Cube's data arrived to complicate the picture in a different direction entirely. The diurnal water cycle that Chandrayaan-1's instruments had detected, water and hydroxyl signals weakening on the sunlit surface at lunar noon, then recovering in the lunar evening, was not a measurement artifact. It was a real behavior, and it was being confirmed from multiple instruments. The surface of the moon, in full sunlight, was gaining and losing water molecules over the course of every lunar day, as though the regolith were breathing in a rhythm timed to the sun. There is no atmosphere to carry that moisture. There is no condensation, and no humidity, no weather of any kind. What was happening, as best the data could support, was that the solar wind, the constant stream of charged particles the sun emits, was delivering hydrogen ions to the lunar surface at a rate of roughly 1 kilogram per second globally. And when those hydrogen ions struck the oxygen-bearing minerals abundant in lunar regolith, they were forming hydroxyl molecules and possibly water directly, in real time, through particle bombardment. The moon was not just hiding ancient ice. It was, in some limited chemical sense, manufacturing water every day in the sunlight, and then losing it again as temperatures climbed past the point where the molecules could remain attached to the surface. The sweating moon, moisture appearing on an airless surface with no conceivable mechanism for it, here created not by climate, but by the sun itself doing chemistry on the rock beneath it. That process explained a signal. It did not explain where the water went after it escaped the daytime surface, or whether any of it migrated toward the poles to be cold-trapped, or how much of the polar inventory came from that daily cycle versus from the ancient comet and asteroid deliveries that the LCR-OSS plume seemed to confirm. The answer was not converging. It was branching. Water was confirmed in one plume, detected as a living molecular presence on the sunlit surface, and still the question of where it was concentrated, on the ground, at the pole, accessible to anything that might one day need it, remained open in a way that only a landing could answer. And so when India announced that Chandrayaan-3 would attempt the first soft landing in the lunar polar region, There was a reasonable expectation that this would be the mission that finally closed the distance between orbital signals and ground truth. Everything prior had been indirect, spectrometers reading absorption lines from hundreds of kilometers above the surface, impact plumes analyzed by a spacecraft flying through debris at 2 kilometers per second, neutron counts that implied hydrogen without ever touching a grain of soil. Chandrayaan-3 would actually land. Its rover, Pragyan, would drive across the surface near the South Pole and press instruments directly against the regolith that all those decades of orbital inference had been pointing toward. This was, by any reasonable measure, and the moment the question should have resolved. The rover found aluminum. It found iron, calcium, chromium, sulfur, and titanium. The chemical fingerprint of the lunar South Pole was rich and detailed, a complete mineralogical portrait of exactly the kind of terrain that orbital data had predicted. And then the analysis stopped, because there was no hydrogen, no water. The most precisely placed instrument package ever deployed in the lunar polar region had examined the ground that every prior mission had been circling for decades, and the one element that justified the obsession was simply absent. And still, the moon gave up nothing. The honest answer is that nobody fully understands why the surface came up dry. The orbital signals had been consistent. The LCROSS confirmation had been direct and chemically unambiguous. The diurnal cycle of water appearing and vanishing with the sun had been confirmed from multiple independent instruments. And yet, the rover's contact with the actual surface produced a mineralogical list that read like every element except the one that mattered. Whether this reflects a genuine absence of hydrogen in the specific patch of ground Pragyan examined, or whether it reflects something about how the water is distributed, or at what depth, or in what chemical form, remains genuinely unresolved. The instruments were working. The surface was right. The answer was missing. But then, the Chasti probe, a thermal measurement instrument aboard the Vikram lander, returned data that began to reframe the entire problem. Chasti measured the temperature of the regolith at the surface and at a series of depths extending down to roughly 10 centimeters. At the surface, the reading was approximately 60 degrees Celsius, warm enough to be uncomfortable, warm enough that if you pressed your palm flat against that soil, you would pull it away quickly. And then, 8 centimeters down, a depth shorter than the width of your hand from the base of your palm to the first knuckle of your middle finger, the temperature dropped to approximately negative 10 degrees Celsius. A swing of 70 degrees over a vertical distance you could cover in a single slow push of a finger into the ground. Sit with what that means for a moment. The surface of the moon, in the sunlit polar region, is hot enough to burn. 8 centimeters below that surface, yet the temperature is colder than a home freezer. You could burn your fingers on the top layer and get frostbite reaching into the soil, at the same spot, at the same time. That is not a dramatic metaphor constructed for effect. That is a measurement. What it describes is an extraordinarily powerful insulating layer, 8 centimeters of loose, porous lunar dust acting as a thermal blanket, so effective that it isolates the shallow subsurface from almost the entire range of the surface temperature. 70 degrees of thermal gradient compressed into a span shorter than a coffee cup is tall, and below that layer, the temperatures are cold enough to approach conditions where water ice mixed into the regolith would be stable for millions of years. This is where the depth pattern becomes impossible to ignore. Luna 24, it drilling 2 meters into the equatorial regolith in 1976, found that the water content in its core sample increased the deeper the drill went, a gradient pointing downward, towards something the surface sample alone would never have revealed. L-Cross, when it struck Cabeus crater, did not excavate surface material. The Centaur stage drove through the top layer and displaced material from below, and what came up in the ejector plume was water that had been sitting beneath the surface, not resting on top of it, and the orbital spectrometers that detected hydrogen signals inconsistent with the trace amounts attributable to solar wind surface chemistry. Those signals implied something more concentrated, something deeper, is something that the surface measurements were not capturing because surface measurements were only reaching the surface. The pattern is the same across every data point that has ever found water on the moon. It points down. Luna 24 points down. L-Cross points down. The orbital signatures point down. And the Chastity temperature gradient explains why. 8 centimeters of insulating regolith is enough to separate the thermal environment at the surface, where water molecules cannot survive the radiation and heat from the environment just below, where they might be locked in place indefinitely, protected by nothing more than a thin blanket of dust too fine to see from orbit. And we haven't even started digging. Every instrument that has reached the moon has either measured the surface or inferred what lies beneath it, and not one has directly sampled the layer that the thermal data now suggests is where the answer lives. Not the deep polar darkness of permanently shadowed craters, but the shallow subsurface lying just below the dust that every rover has been driving across. The water might be closer to the surface than the depth of a coffee cup, centimeters, not kilometers, not the depth of a well or the floor of a crater. Centimeters of dust, thin enough to seem insignificant, thick enough to have hidden the answer from every instrument we have sent. That same dust, the material that may be covering the most valuable substance on the moon, turns out to have a character of its own that nobody was prepared for. That dust, the same material that acts as a thermal blanket over the shallow subsurface. The same loose powder that the Chastity probe's measurements now suggest may be insulating ice-bearing regolith just centimeters below the surface. That dust is not simply an engineering inconvenience sitting on top of the answer. The same dust that hides the answer may also be the most dangerous substance ever contemplated for sustained human contact. But before reaching the dust's full character, there is a more immediate problem, and it sits with the question of whether better instruments can simply see past all of this. That assumption, that the detection challenge is technological, that more sensitive sensors will eventually dissolve the ambiguity, seemed reasonable for decades. And then, in 2022, a spacecraft called the Korea Pathfinder Lunar Orbiter carried into orbit around the moon a camera unlike anything previously flown. It was called ShadowCam, and it was built for one specific purpose: to image the terrain inside permanently shadowed regions using only the faint reflected light that bounces off surrounding crater walls and ridges. Not the sun, reflected ambient light, the kind of illumination you might find at the bottom of a very deep stairwell. And it worked. ShadowCam returned the highest resolution images ever taken inside a permanently shadowed crater: boulders, slopes, textures in the regolith, geological features that had never been seen because no instrument had ever been sensitive enough to capture them. There was no obvious ice, no reflective patches, no frost sheets coating the floor, no gleaming deposits suggesting a frozen lake sitting in the permanent cold. What ShadowCam found was regolith, the same fine, unremarkable-looking powder that covers the rest of the lunar surface. We can now see inside the darkness for the first time, and the ice is still hiding, not because the cameras failed, but because the ice, if it is there, is not pooled as a visible deposit, the way water freezes in a terrestrial environment. It is almost certainly mixed into the soil grain by grain, distributed throughout the regolith matrix, the way moisture is distributed through wet sand, present in the structure, not resting on top of it, which means you cannot see it from orbit. You cannot see it from the surface. You can only find it by digging. And digging in a permanently shadowed crater on the moon is not a matter of building a better shovel. Permanently shadowed regions are, in terms of the combined environmental hazards they present to both machinery and human beings, the most hostile terrain we have ever seriously proposed entering. The darkness is absolute and permanent. Solar power, which is how nearly every lunar mission has sustained itself, does not function inside a crater that has not seen sunlight in 3.5 billion years. The temperatures approach absolute zero in ways that cause metals to contract, lubricants to fail, and electronic components to behave unpredictably. The terrain is rough. ShadowCam confirmed that. Steep slopes, embedded boulders, uneven regolith that has never been mechanically disturbed, and none of it mapped with the ground-level precision you would need to navigate a rover or a suited human being safely. Every system that depends on line-of-sight communication loses contact the moment it descends into a crater deep enough to qualify as permanently shadowed. The proposed solution to the power problem is to operate from the crater rim. specifically from what researchers call peaks of eternal light, the high ridges and elevated terrain surrounding craters like Shackleton, where the geometry of the sun's very low angle at the lunar poles means certain points receive near constant illumination. On the rim of Shackleton crater, temperatures hover around -50 degrees Celsius, roughly -60 degrees Fahrenheit, bitterly cold by any terrestrial standard, but thermally stable and reachable by solar-powered systems. The vision is a base on the sunlit rim sending robotic equipment down into the dark below, tethered back to the light like divers descending from a boat. It is an elegant engineering concept. It is also a concept that requires every piece of equipment descending into that cold, dark terrain to function reliably in conditions that have defeated machinery before, and to do so while covered, within hours of the first descent, in the same fine powder that has been waiting at the bottom of that crater, undisturbed for billions of years. The dust. Every mission that has landed on the moon has encountered it. Every astronaut who has stood on the lunar surface has brought it back inside. The 12 human beings who walked on the moon during the Apollo program, all of them, yet without exception, reported respiratory irritation or eye irritation following their surface excursions, and those excursions lasted hours, not days, not weeks, hours of exposure to lunar dust, and every single one of them had a physical reaction. That is 100% of the human beings who have ever stood on another world reacting to the ground beneath their feet. To understand why, you have to understand what the dust actually is at a physical level, because it does not behave like any dust you have encountered on Earth. Terrestrial dust particles, the kind that settles on furniture, the kind stirred up by wind, have been tumbled and abraded by water, by weather, by the constant mechanical collision of billions of years of geological processes. Their edges are rounded. They are, in relative terms, smooth. A lunar dust has experienced none of this. It has never been touched by liquid water. It has never been shaped by wind. What has shaped it is impact. Billions of years of micrometeorite strikes, each one vaporizing and resolidifying tiny fragments of the lunar surface into particles with edges that are not rounded but fractured, razor-sharp at a microscopic level, comparable in their geometry to freshly shattered glass. Imagine grinding a window into powder so fine it floats in the air, then making each particle electrostatically sticky so that it clings to whatever surface it contacts. Fabric, metal, skin, the interior of a lung. That is what lunar dust is. And it is everywhere. Every step a rover takes, every boot that presses into the regolith, sends it drifting in the low gravity and near vacuum, settling on solar panels, embedding in mechanical seals, abrading suit materials that were designed to resist it. The Apollo astronauts' suits were visibly degraded after a single moonwalk. Zippers became difficult to operate. Helmet visors were scratched. The engineers had known the dust would be a problem. They had not known how comprehensively it would attack every surface it contacted. And then there are the biological consequences, which are where the word problem stops being adequate. Laboratory studies exposing human lung cells to simulated lunar dust, material engineered to replicate the composition and surface chemistry of real regolith, found that within 24 hours, up to 90% of those cells were dead, not damaged, not stressed, dead. Let that number settle for a moment. 9 out of 10 cells, not from a toxin engineered to kill, and from the ground. The explanation lies in the surface chemistry of the particles themselves, which have spent billions of years under unshielded solar radiation and cosmic ray bombardment, a process that leaves their surfaces chemically reactive in ways that terrestrial silica dust, the material responsible for the mining disease silicosis, simply is not. When those particles reach the moist tissue of the lung, the reaction they trigger is more destructive than anything produced by the comparatively weathered particles a miner breathes. And the studies of animals inhaling regolith simulant over extended periods showed that the damage does not stabilize. It accumulates, worsening progressively over weeks of continued exposure, the inflammation deepening, the lung tissue increasingly compromised with each passing week. The dust doesn't stop at the lungs. The smallest particles, submicron fragments too fine to be captured by the upper respiratory system's defenses, traveled in rodent inhalation studies from the nasal passages directly to the brain along the pathway of the olfactory nerves. The same dust that hides the answer is also the same dust that, given sufficient exposure, works its way through the body's deepest defenses by the most direct route available. The lunar surface, considered as an environment for the human beings who would need to dig into it, is not hostile in a single dimension that engineering can address. It is hostile in every dimension simultaneously: the cold, the darkness, the terrain, the absence of power, and now a ground cover that attacks machinery mechanically and human tissue at a cellular level. And the treasure and the trap occupy the same coordinates on the map. And the dust problem is not yet fully described, because the electrical behavior of the lunar surface adds a dimension to it that nobody anticipated until the Apollo astronauts looked up at the horizon during twilight and saw something that should not have been there. And the brain finding is where that description finally breaks down entirely, because what we are talking about is no longer a respiratory hazard that a better filtration system could address. The finest particles of lunar dust, the submicron fragments at the lower end of the size distribution, particles roughly 50 times thinner than a single human hair, are too small to be caught by the upper respiratory tract's defenses. They pass through. In rodent inhalation studies, those particles did not stop at the lungs. They traveled from the nasal passages directly to the brain along the pathway of the olfactory nerves, the same neural channel through which the brain processes smell. That route bypasses the blood-brain barrier, one of the body's most fundamental protective mechanisms, entirely. Sit with that for a moment, because the implications deserve the time. We are not talking about a particle that damages tissue on its way in and stops there. We are talking about a particle that, in animal models, completes the journey from the outside world to the interior of the brain without a physical barrier stopping it. And remember what these particles are made of: silicates and metal oxides whose surfaces have been chemically altered by billions of years of unshielded solar radiation and cosmic ray bombardment, leaving them reactive in ways that ordinary terrestrial silica dust is not. The silica dust that causes silicosis in miners has at least been partially weathered by contact with air and water over geological time, its sharpest chemical edges dulled by exposure. Lunar dust has experienced none of that. Its surfaces are essentially the freshest version of those compounds that can exist, never rained on, never oxidized in an atmosphere, never touched by anything that would reduce their reactivity. When those surfaces contact biological tissue, the damage they produce reflects that freshness. And the rodent studies showed that the lung damage from continuous inhalation did not plateau at some tolerable level. It worsened progressively over the full 13 weeks of the study period, each week's measurements showing deeper inflammation, more compromised tissue, no sign of the body adapting or the injury stabilizing. The same dust that hides the answer is the same dust whose finest particles, in animal models, do not stop at the lungs, but follow the olfactory pathway upward, arriving at the brain through a route the body has no mechanism to close. No suit redesign eliminates this entirely. A suit can be sealed more tightly, its seals improved, its filters made finer, but any mission that involves sustained surface operations, drilling, excavating, or operating machinery that disturbs the regolith over weeks and months, generates dust continuously, and the history of the Apollo missions established that lunar dust finds its way into every enclosed space eventually. It migrated inside the landers. The astronauts brought it in on their suits after each moonwalk, and the volume of time they spent on the surface was measured in hours. The volume of time a permanent crew would spend on the surface to actually extract water from the regolith is measured in months. But the dust threat does not end with biology, because the lunar surface has another property that was not understood until the Apollo astronauts themselves provided the first evidence for it, by noticing something at the horizon that had no straightforward explanation. During the twilight period just before lunar dawn and just after lunar sunset, the brief interval when the boundary between light and dark, the terminator, passes over a given location, several Apollo crews reported seeing a faint glow along the horizon. not a reflection of sunlight from some elevated feature, not an artifact of their visors, a glow that persisted, hovering just above the surface, faint but real. What they were seeing was dust, not settled dust, not stirred dust, dust that was floating, electrostatically levitated off the surface by the same boundary they were observing. The terminator is not just a lighting division, it is a zone of extreme electrical tension. The sunlit side of the moon is continuously struck by solar ultraviolet radiation, which ejects electrons from the surface through a process called the photoelectric effect, leaving that side positively charged. The dark side accumulates electrons from the solar wind, leaving it negatively charged. At the terminator, where these two regimes meet, the voltage differential between the illuminated and shadowed ground can reach hundreds of thousands of volts. Imagine the potential difference between 2 points you could walk between in a few steps, not the voltage difference between a power line and the ground below it, but an order of magnitude beyond that, concentrated across a physical boundary you could cross on foot. That field is powerful enough to do something that seems almost impossible on a world with no wind. It lifts particles off the ground, the finest dust grains, already electrostatically charged from constant radiation exposure, respond to the field gradient at the terminator and levitate, rising above the surface and drifting horizontally along it. What the Apollo astronauts saw glowing on the horizon was that process made visible, a faint luminous haze of electrically suspended glass shards, catching the last or first light of a lunar day. And because the terminator moves, sweeping across the entire lunar surface over the course of every month, this is not a localized or occasional phenomenon. It is continuous and global. More specifically, it happens at the precise boundary that any crew operating a solar-powered base near the poles would need to cross repeatedly, the line between the sunlit rim where power is available and the permanently shadowed interior where the water is. Every transit from illuminated ground into a permanently shadowed crater means crossing that electrostatic boundary. Every piece of equipment, every suit, every dust particle clinging to every surface would encounter that voltage differential. The charged dust that rides those fields does not simply float and then resettle where it started. Studies of its behavior suggest it drifts, carried by the field gradients, from illuminated regions toward shadowed ones, potentially accumulating on crater floors over time, layer by layer, adding to the insulating blanket of regolith that already covers whatever lies beneath. In 2025, a Firefly Aerospace's Blue Ghost mission successfully tested an electrodynamic dust shield on the actual lunar surface, a device that uses oscillating electric fields to drive charged dust particles off a surface, clearing a camera lens and a radiator panel during the mission. It worked. The particles moved. It is an early proof of concept, a demonstration that the electrical nature of the dust can be turned against itself in a small, controlled way. But clearing a camera lens and excavating water ice from under meters of electrostatically active, biologically lethal regolith in permanent darkness at -240 degrees are not problems separated by a few engineering generations. They are problems separated by an entirely different order of difficulty, and the gap between them is not yet bridged. The ice might be real, and the danger is certainly real, and that combination, a resource that could change everything about what humanity can do beyond this planet, locked inside conditions that attack machinery, suits, lungs, and by the most direct route available, the brain itself, is where the story stops being about science entirely and starts being about something else. And the something else is not abstract. It has a price tag attached to it. And the price tag is the first thing that makes the full weight of the situation land. Getting water to the lunar surface from Earth costs somewhere between $10,000 and $50,000 per kilogram, depending on the mission, architecture, the launch vehicle, and the exact destination. That range sounds technical, so set it aside for a moment and reduce it to something you can hold in your hand. And a single liter of water weighs 1 kilogram. A single liter, the amount in a standard water bottle, the amount a person drinks in a couple of hours on a warm afternoon, the amount you might use washing your hands twice, delivered to the lunar surface from Earth, would cost as much as a high-end laptop computer, and potentially as much as a used car. Not a shipment of water, not a month's supply, one bottle. And that is before the water does anything except exist on the surface, before it is consumed or processed or converted into anything else, before a single person takes a single sip. That is just the cost of transit. A permanent lunar base requires water continuously, for drinking, for hygiene, for growing food in closed-loop agricultural systems, for cooling equipment, for replenishing oxygen in the atmosphere that crew members breathe inside every sealed habitat and every pressurized suit. The volumes involved are not small. The arithmetic, run honestly, leads to a number that makes any serious long-term presence on the moon economically impossible if every liter has to be launched from Earth's surface. This is where the nature of what was found in those permanently shadowed craters shifts entirely. Because water is not just water up there. Water is oxygen. When you run an electrical current through liquid water, a process called electrolysis, straightforward enough that it is demonstrated in high school chemistry classes, the molecule separates into its two components, 2 atoms of hydrogen and 1 of oxygen. Both gases can be stored cryogenically. Both gases, when combined and ignited, produce one of the most energetically efficient chemical reactions available to rocket propulsion. The RS-25 engine that powered the Space Shuttle main engines burned liquid hydrogen and liquid oxygen. The RL-10 engine, used in multiple upper stages across several decades of American spaceflight, burns the same combination. These are not experimental propellants. They are among the most flight-proven fuel combinations in the history of rocketry. And their raw ingredients are the 2 atoms in every water molecule sitting at the bottom of those craters. A functioning extraction and electrolysis plant near the lunar South Pole would not just supply drinking water to a crew. It would supply rocket propellant. It would supply breathable air. It would supply the cooling medium for thermal management systems. It would, and in a single installation, close most of the logistical loop that currently makes sustained human presence beyond Earth dependent on constant resupply from the bottom of a very deep gravity well. And the gravity well is the other half of the equation, because the moon's surface gravity is 1/6 of Earth's, and that difference is not cosmetic. Escape velocity from Earth's surface is approximately 11.2 kilometers per second, the speed a rocket must achieve to leave Earth's gravitational influence entirely. Escape velocity from the lunar surface is approximately 2.38 kilometers per second. That means launching from the moon requires roughly 1/5 the velocity needed to launch from Earth. And because the energy required scales with the square of the velocity, yes, the practical difference in fuel consumption is not a factor of 5. It is dramatically larger. A spacecraft that refuels at a lunar depot before heading toward Mars carries a fraction of the propellant mass it would need if it launched fully fueled from Earth, which means it can carry more actual payload, more equipment, more supplies, more everything that makes a mission viable. The moon, positioned where it is, with the gravity it has, is not just a destination. It is a natural platform, a logistical node already placed by orbital mechanics at the first step outward from Earth, where propellant made from local water could be waiting for ships on their way to Mars, to the asteroid belt, to anywhere the solar system has to offer. Yeah, the analogy that comes closest is the highway gas station. You could theoretically drive across a continent with every drop of fuel loaded onto the roof of your vehicle before you left the driveway, but no one does, because a network of stations along the route makes the journey economically and practically rational in a way it would not otherwise be. Going to Mars without lunar refueling is that roof-loaded drive. Except the journey is hundreds of millions of kilometers, and there is no shoulder to pull over on if something goes wrong. What felt like an engineering problem a few minutes ago now looks like something closer to a siege. The question is no longer whether water exists. It is whether we can survive the ground long enough to reach it. And in 2024, the United States cancelled the one mission specifically designed to answer that question. The Volatiles Investigating Polar Exploration Rover, VYPER, was a rover built with a 1-meter drill, explicitly designed to move across the lunar South Pole. sample the soil at multiple depths and locations, and determine whether the ice distributed through that regolith was actually accessible, whether it existed in concentrations and forms that extraction technology could work with. It was the only dedicated ice prospecting mission with a drill in the Western Development Pipeline, and not one of several parallel efforts, the only one. NASA cancelled it due to budget overruns and schedule pressures before it launched, before the rover touched the lunar surface, before a single core sample was pulled from the ground beneath a permanently shadowed crater. The same dust that hides the answer, packed, insulating, electrically active, biologically hostile, had become a kind of metaphor for the situation itself. The resource and the obstacle are the same material, and the tool we built to push through it was set aside before it could be used. A gold rush town that decided it could not afford the pickaxes. The ice may be there, the propellant may be there, the oxygen may be there, and the economic foundation for everything humanity wants to do beyond this planet may be sitting in the dark at the bottom of craters we can now image but have never drilled. And the only question that drilling could have answered remains, for now, unanswered. If lunar water is this consequential, if it is fuel and oxygen and the economic logic that makes deep space viable, then the question of who reaches it first is not academic. It is strategic, and the race is already underway. Billions of dollars, dozens of missions, 2 superpowers. And the question they are all betting on still does not have a clean answer. There is something quietly unsettling about a species that identifies the most important question it needs to answer, builds the tool to answer it, and then decides it cannot afford the tool. Yet the cancellation of Viper did not happen in a vacuum. It happened in the middle of a race that has been accelerating for the better part of a decade, that involves not just national space agencies, but private companies, international coalitions, and competing legal frameworks, all converging on the same few square kilometers of terrain at the bottom of the solar system's most strategically positioned body. The assumption that space exploration is a cooperative scientific endeavor, that the countries involved are essentially colleagues working toward a shared human future, is a comfortable assumption. It is also, at this particular moment in history, not quite accurate. Consider what has happened in the last 2 years alone. In May of 2024, China launched Chang'e 6, and the mission traveled to the far side of the moon, the side that permanently faces away from Earth, the side no lander had ever successfully sampled, descended into the South Pole Aitken Basin, one of the oldest and deepest impact craters in the solar system, collected material from the ancient lunar floor, and returned those samples to Earth. No other nation has done that. Not the United States, not Russia, not any of the 17 nations that have contributed to one program or another. China reached the far side of the moon, picked up rocks from terrain no human instrument had ever touched, and brought them home. That is not a scientific curiosity. That is a demonstration of deep space capability, and it was followed almost immediately by announcements about what comes next. Chang'e 7 is planned for 2026, and it will carry a lander, a rover, and something genuinely unusual, a small flying probe designed to lift off from the main lander and hop into the permanent shadow of a polar crater, approaching the darkness from above rather than driving into it along the surface. The flying probe is a direct response to the problem that ShadowCam could see inside the craters but could not touch them, and that surface rovers risk losing power the moment they enter permanent shadow. If you cannot drive in and you cannot see in clearly enough, you send something that drops in from above, samples what it finds, and returns. 3 years after that, Chang'e 8 is planned for 2029. It with an explicit mandate to test in situ resource utilization, including the ability to take lunar regolith and 3-dimensionally print structural material from it. If you can print structures from the ground beneath your feet, You do not need to ship buildings from Earth, and the economics of establishing a permanent presence shift in ways that are difficult to overstate. The International Lunar Research Station, the program China is leading, targets a robotic base by 2030 and crewed capability in the mid-2030s, with 17 partner nations already committed. On the American side, the Artemis program targets a crewed South Pole landing. Artemis 3, somewhere between mid-2027 and late 2028, which would be the first human footprints on the lunar surface since Apollo 17 in 1972, a gap of more than 55 years. A semi-permanent base is planned near Shackleton Crater for 2028 to 2030, positioned on a sunlit ridge adjacent to the permanently shadowed regions, standing in near constant light while looking directly down into ancient, unbroken dark. The Artemis Accords, signed by dozens of nations as of 2025, assert that extracting space resources does not constitute national appropriation of the moon itself. China and Russia have not signed them. What you have, then, are two parallel lunar infrastructure programs, two competing legal frameworks for what resource use means and who it belongs to, and two timelines that converge on the same destination within roughly the same window of years. Now think about the terrain they are converging on. The viable corridors for a polar base are not large. A location must offer near constant sunlight for power generation, reasonably flat and stable ground for safe landing and construction, and close proximity to the ice-bearing permanently shadowed craters. These three requirements do not overlap everywhere. They overlap in a handful of narrow ridges and rim segments. Places like the Shackleton Rim, which sits in near constant light while the crater floor below it has not seen sunlight in billions of years. The entire strip of terrain that satisfies all three conditions simultaneously might be something you could walk across in 20 minutes. Think about that as a physical space, and not a continent, not a territory, a neighborhood. A ridge thinner than a neighborhood, and the entire future of off-world fuel production, oxygen generation, and deep space infrastructure may depend on who builds there first. This is what the Oklahoma land rush of 1889 looked like from the inside. A starting gun, a fixed amount of desirable territory, and the understanding that the best positions would be claimed in the first hours. No one formally owned the land before the rush. No one formally owns the moon now. The Outer Space Treaty of 1967 prohibits national sovereignty over celestial bodies, and that prohibition is real and binding. But sovereignty and presence are not the same thing. The first base built on a prime ridge does not own the ridge. It simply occupies it. And the infrastructure that follows, the power stations, the fuel depots, the communication relays, the processing facilities, does not need to claim the ground to control access to it. Think of the first railroad through a mountain pass. No nation owned the mountain, but whoever laid the track first determined the route everyone else would have to use. The first power cable run from a solar array on the Shackleton Rim to a processing unit at the crater's edge is a railroad track. The first water electrolysis facility drawing hydrogen and oxygen from extracted ice is a railroad track. You do not plant a flag and declare a border. You build the thing, and then the thing is there, and the next arrival has to decide whether to build next to it or find a narrower ridge somewhere else. Alongside the two superpowers, private companies are pressing forward with their own polar-targeted hardware. Intuitive Machines has already landed a spacecraft near the lunar South Pole. Astrobotic, Blue Origin, Firefly Aerospace, and Lunar Outpost are all developing systems aimed at the same region. India, building on the success of Chandrayaan-3, has expressed interest in future polar extraction missions. Japan and the European Space Agency have their own polar exploration timelines, typically aligned with one coalition or the other. The Shackleton Rim is becoming crowded on paper before anyone has placed so much as a single anchor in the ground. And we haven't even started digging. Every program, every lander, every rover, every coalition agreement, they are all predicated on the assumption that the ice in those craters is accessible and that it exists in concentrations workable enough for extraction technology to engage with, that the ground will yield what the instruments have been suggesting for 3 decades. That question has not been answered. The one rover built specifically to drill for the answer was cancelled before it flew. What remains is a race toward terrain no one has physically proven can deliver what the race is for. And yet, for all the urgency, for all the coalition agreements and cancelled rovers and geopolitical manoeuvring over ridgelines thinner than a neighbourhood, the thing that keeps getting lost in the noise of the race is something quieter and considerably more unsettling. The prize has not been confirmed, not in the way that matters, not in the way that allows an engineer to sit down, open a design document, and write down a number for how many kilograms of extractable ice exist per cubic meter of regolith at a workable depth. That number does not exist yet. And the reason it does not exist is one of the strangest scientific paradoxes of the space age. Every instrument we have ever pointed at the moon has come back telling us the same thing. The water is there. The orbital spectrometers on Clementine in 1994 detected conditions consistent with ice in permanently shadowed regions. Lunar Prospector's neutron spectrometer mapped hydrogen concentrations at both poles in 1998, suggesting somewhere between tens of millions and hundreds of millions of metric tons of hydrogen-bearing material at the moon. Mineralogy Mapper aboard Chandrayaan-1 confirmed hydroxyl and water molecules distributed across the sunlit surface in 2008. L-Cross drove a 2.5-ton rocket stage into Cabeus crater at nearly 2 kilometers per second in 2009 and watched the resulting plume carry water vapor, hydrogen, ammonia, methane, and carbon dioxide back into the light. The signals are not ambiguous. The signals are not the product of wishful interpretation. They form a consistent body of evidence assembled across 5 decades and a dozen separate missions, and they all point in the same direction. And still, every time we land something on the surface and put instruments directly into the soil, the moon hands us a fistful of dry dust. It is a strange kind of conversation to have with a world. Every mission is like asking the moon a direct question, and the moon always answers, but never the question you actually asked. You send an orbiter and ask whether there is water, and the moon says there is hydrogen. You send an impactor and ask whether there is ice, and the moon says there was vapor. You send a lander to the most promising crater rim on the entire surface, a lander built specifically to go to the spot where everything the instrument said should be true. And you ask whether you can finally reach out and touch what 3 decades of orbital data have been pointing at. And the moon hands you dry regolith, a thermal profile that drops 70 degrees in the space of 8 centimeters, and silence where a hydrogen signal should be. Luna 24 returned a sample in 1976 that carried moisture increasing with depth. It was ignored as contamination. Chandrayaan-3's Pragyan rover found aluminum, iron, calcium, chromium, sulfur, and titanium in the South Polar soil. It did not find hydrogen. It did not find water. And still, the moon gave up nothing. The question that has been building quietly behind all of this, the question that every geopolitical strategist and mission planner is choosing not to dwell on publicly, is whether the instruments are contradicting each other because the water is genuinely there but genuinely unreachable by anything we have yet landed on the surface. Because there are explanations, serious, scientifically plausible explanations, that do not require the data to be wrong. The first is dispersal, and the ice may not exist as concentrated deposits, as seams or sheets or frost patches that a drill could encounter, and a processing unit could extract at meaningful rates. It may instead be distributed grain by grain through the regolith, the way moisture distributes itself through wet sand. Present everywhere, concentrated nowhere, inaccessible to anything short of processing enormous volumes of material to recover trace amounts. ShadowCam, the instrument aboard the Korea Pathfinder lunar orbiter launched in 2022, imaged permanently shadowed region floors in unprecedented detail using light reflected off nearby crater walls and peaks. Some models had predicted that ice deposits, if present in quantity, should appear as reflective patches against the dark regolith. ShadowCam found no such patches. Oh, the floors looked like floors, dark, rough, undifferentiated, and still, the moon gave up nothing. The second explanation is depth. The moon's regolith acts as a thermal insulator, and what Chandrayaan-3's temperature probe found, surface temperatures around 60 degrees Celsius dropping to nearly -10 degrees at 8 centimeters, suggests that the thermal environment changes radically within a very short vertical distance. In permanently shadowed regions, the same insulating property works in reverse, trapping cold rather than heat, but the principle holds. The surface is not the subsurface. The water table, if that analogy is useful, may sit below the layer that every lander so far has been able to sample. Think of it as an aquifer. The water exists, and the instruments above ground have been detecting it accurately. But every mission so far has been trying to drink from the surface of a desert without knowing that the oasis begins 3 meters down. VIPER was built with a 1-meter drill, which would have reached deeper than any previous surface instrument, and it was cancelled in 2024 before it flew. The one purpose-built tool for answering this specific question was identified as the most important instrument we could send, and then we decided we could not afford to send it. The third explanation is chemistry. Some fraction of the water detections, possibly a significant fraction, may not represent free ice at all, but water molecules chemically incorporated into mineral structures are bound tightly enough that extracting them requires energy and processing equipment far beyond the simple heating and collection systems most early ISRU concepts assume. If the water is chemically bound rather than frozen, the extraction problem is not a drilling problem. It is a chemistry problem, and it is a harder one. None of these explanations rule out the others. The honest answer, the one that sits underneath every mission architecture document and every coalition agreement and every private company prospectus, is that all three may be true simultaneously in different proportions that we do not yet know. Chang'e 7, planned for 2026, intends to send a flying probe into a permanently shadowed region to collect samples directly, which would be the first direct contact with PSR material in history. Our Artemis 3 aims to place astronauts near the Shackleton Rim sometime between 2027 and 2028, and those astronauts would carry instruments capable of deeper sampling than any robotic precursor. Future private missions are developing SATA-ISRU demonstration hardware. But none of these missions carries a proven system for extracting usable water from lunar regolith at scale. They are the next generation of questions being asked of a world that has been answering questions for 50 years without ever quite answering the right one. The race toward the South Pole is real. The geopolitical stakes are real. The physics of what accessible lunar ice would mean for deep space infrastructure is real. Every part of the architecture, the fuel depots, the oxygen supply, the permanent bases, and the Mars staging points, is built on a foundation that has been rigorously confirmed from above and consistently elusive from below. 50 years of instruments all agree. The water is there. 50 years of landings all report. Not here, not like this, not yet. The universe, it turns out, is not obligated to place its most valuable resources in a form that suits our current tools. And yet, we kept asking. that is the part of this story that deserves to be held for a moment before anything else is said. Not the silence of the moon, not the contradictions in the data, not the geopolitical tension gathering around a handful of permanently dark craters, but the simple fact that for 50 years, across generations of scientists and engineers and mission planners on several continents, the answer kept coming back incomplete, and the response was always another mission. Luna 24 came back from the lunar surface in 1976 with 170 grams of soil and a faint signal of water buried in the data. And the scientific community looked at it and decided the most likely explanation was contamination. A signal that turned out to be real was set aside for nearly 2 decades. And still, the moon gave up nothing, not because the water wasn't there, but because the tools and the assumptions of the moment weren't ready to receive what the moon was actually saying. Clementine mapped the geometry of the South Pole in 1994 and found conditions that looked exactly right. Permanent shadow, preserved cold, the physical architecture of a place where ice should survive. Lunar Prospector arrived 4 years later. He swung its neutron spectrometer over the poles and found hydrogen in quantities that pointed toward hundreds of millions of metric tons of water. When it exhausted its fuel in 1999, mission controllers aimed it into a shadowed crater, hoping for a plume that would confirm everything. The crater absorbed the spacecraft like a stone, dropping into deep water, and the answer, once again, did not come. L-Cross finally produced the plume in 2009, and the plume held water vapor, and for a brief moment it seemed like the question had been settled. Then Chandrayaan-3 landed near the South Pole in 2023, and the surface instruments found no hydrogen, no frost, no indication of water anywhere a hand could reach. Every mission answered something. None of them answered everything. And you ask whether there is water, and the moon says there is hydrogen. You ask whether the hydrogen is ice, and the moon shows you vapor in a plume. You ask whether the ice is accessible, and the moon hands you a fistful of dry dust and waits. The moon did not owe us an easy answer. Nothing in the universe does. The remarkable thing is not the silence. It is that we kept sending machines into that silence and listening. More carefully each time, with better instruments each decade, with coalitions of nations that hadn't existed when the first probe flew. The moon gave up nothing easily, but we kept asking. And so you find yourself back at the edge of that crater, the one we stood at when this began, looking down into a darkness that has not changed in 3.5 billion years. But you are not the same person who first looked over that rim. You know now what that darkness holds. Not a clean answer, not a vault whose combination has finally been discovered, but something more complicated and more human than that. A question that has driven 5 decades of missions and hundreds of scientists and the competing ambitions of nations that could not agree on much else, all of them leaning forward over the same dark edge, asking the same thing in different languages, with different instruments in different decades, and none of them quite getting all the way to the bottom. The ice may be there right now, just centimeters below the surface your boot would press into if you stood there, just slightly deeper than the instruments we have sent so far have managed to reach. The Chastity probe on Chandrayaan-3 found a temperature swing of 70 degrees across the depth of a coffee cup, burning at the surface, cold as a different world just a few centimeters down. The depth pattern points inward and downward, as it always has, as suggesting that whatever is preserved here is preserved just out of reach, patient in a way that nothing we build quite manages to be. The answer may not be distant in the way that stars are distant. It may be close in the way that something buried just beneath the ground is close, present, real, waiting for a shovel that goes one layer deeper than the last one we sent. And someone is building that shovel right now. That is the last thing this darkness is. Not emptiness, not a dead end, but an invitation that has been sitting open for 50 years, addressed to whoever is willing to go back one more time. The story does not end at the crater's edge. It always begins there,